So today we continue the May-Leonard model. We talked about reduction to a normal form last time. So let me recap this. Our goal was to start from this equation of motion for three species, which is reducing to a complex Ginzburg-Lambda equation. The way we did this was to first say, let's write this one here in a Jordan normal form. That means write it in terms of the eigenvector spaces, where J is the Jacobian of the linear behavior close to a fixed point, and H of Y are the nonlinearities. Once you are in this base state of the eigenvectors, you can then account for the fact that there is one fast direction and there's this slow manifold that we called M. And I showed you or quoted how you actually find the slow manifold. And once you have the slow manifold, you can write the equation on this slow manifold in terms of the linear part and some nonlinear parts. And they're just, indicated here conceptually. And as you see, these are complicated functions in general, depending on second order and third order terms of YA and YB. And there's a method I told you by which you can reduce the nonlinear form to the simplest nonlinear form. And this is called the normal form of the problem. We found a nonlinear transformation from the Y's to the Z's. And then we could write it in terms of the Z variables, and that is the complex Ginzburg-Lambda equation that you see here in the top slide. Right? So that was where we were at. Now you can just list the parameters that you have when you do this. So along the way, this is all the parameters of the complex Ginzburg-Lambda equation. And that's not a minor thing, that's actually quite important because we derived those parameters. And now we quantify really what this complex Ginzburg-Lambda equation is. It's not a phenomenological set of parameters, it's really given in terms of the microscopic parameters. And those microscopic parameters are the two rates, mu and sigma, that account for contest competition and scramble competition. So that's important that we have this list of parameters given in terms of microscopic values. And one thing you should note is there's 1, 2, 3, 4 parameters in the complex Ginzburg-Lambda equation, but our actual model had only 2, namely mu and sigma, and therefore you can express these 4 variables in terms of 2 microscopic parameters. As we did for the limit cycle calculations, you can write the complex number Z in terms of the amplitude and the phase phi. And when you do that, then this equation here reduces to a quite simple form. It is a form which has a limit cycle at a ratio of C1 to C2, square root of it, and it has a frequency that's modified by the term depending on the radius in this slow manifold. All right, so that's how far we got, and in principle you can do similar kind of analysis for related systems if those systems have some kind of slow manifolds. Now let's go back to the spatially extended system, which has, in addition to the reactions, also diffusion. That means switching of particles between sites, and there I showed you that this has these nice spiral waves, and the spiral waves change in terms of frequency and wavelength as you vary the diffusion coefficients. It also changes as you vary the rates, mu and sigma, And that's something you can explore then by the equations that we study now. So how do you do that? Well, first and foremost, there's a few steps I kind of swept under the rug. The model, how we define it, is a stochastic model because it's talking about rates of things competing and killing, rates of getting born. So it's a stochastic model, and when you simulate the stochastic model using a proper algorithm called Gillespie algorithm, then you get these kind of spiral waves, which are a bit grainy, right? This is not a real continuous field. It's more like a spotty pattern. And the spotty pattern, in the end, if you just look at large enough systems, converges towards a mean field equation. And that's the one you write down when you write a diffusion reaction equation. There you say A is a density as a function of R in 2- or 3-dimensional space. And all these terms here are continuous functions, not absolute numbers of individuals living at a particular site. So that's the description level you have. So you basically take the rate equation that I wrote down in our last lecture and add to it a diffusion term, assuming that the diffusion coefficient for all the 3 different species is the same. Again, for simplicity, you can make the model richer if you change to a system where diffusion coefficients would be different for all the 3 different species. Then you say, well, I've done the reduction to a normal form on the slow manifold, and because this is diagonal, I will get the same kind of diffusion coefficient also for the variable on the slow manifold. Okay? That's our equation now. That's the one we would like to solve. And let me do this with you on the board. So we have the reaction diffusion equation for the May-Leonard model, which is of that form. It's a diffusion term of all the 3 species plus a reaction function. And what we have done is we have reduced it to an equation for a complex variable that also has a diffusion term, and it does have the standard Ginzburg-Landau structure with complex terms. All right. What we would like to do now is to see how far such a description can get us in explaining what you see here. And what you saw there, maybe I repeat the movie, then you see as a function of diffusion coefficient, there's a certain wavelength. And let's call it lambda. And we would like to know what is that wavelength that you see here, and how does this wavelength depend on diffusion coefficient and on the 2 rates. If I run the movie, then you see this also has a frequency, omega, and also if you look at the front, so just focus here on one of the fronts, say the yellow one, then you see it spreads. It has a spreading velocity. So phi v spread. And we would also like to know how does that depend on the diffusion coefficient and on the rates. Good. So how would you calculate that? Well, the system here is simple in a way that the fixed point that you have for this model in the slow manifold is just z equal to 0. And that means when we look at the spreading fronts in the May-Leonard model, in the complex Ginzburg-Lambda model, that's spreading complex amplitudes into a region where you have 0 for your complex amplitude. And you want to calculate then in those systems, so let's say take a cut in space, and you have some kind of front, and this is the amplitude of z, then this is spreading into the regime where z is equal to 0, and you want to know what's the velocity of that spreading front. Now, because you have this spreading into a regime of 0 value, you can use the linear theory to do the calculation. Right? That's the point. So here, in this regime, we can focus on the linear theory to get an idea of how fast this front is spreading. So let's calculate this linear spreading velocity, and let me explain how the logic of that calculation works. So the logic is as follows. We linearize the equation, and in the linearized form, I keep, of course, the Laplacian for diffusion, and from the Ginzburg-Lambda terms, I only need the linear ones. Once you have a linear equation, you go about solving that by Fourier transformation. That is, you define a Fourier transform set of k and t equals the integral over R with a phase space, with a phase factor e to the I kr set of R and T. And you make an ansatz that your set of k and t is some amplitude z hat of k, and I'll take a solution that has a dispersion relation that I call omega of k. So in the same way as we do all these linear stability analysis, we make an ansatz where we take a solution with a dispersion relation. Well, you can insert then this into this equation, right, and combine it, and from that you do get the dispersion relation for the problem. This then gives you omega of k is the base frequency plus I C1 minus the k squared. So this dispersion relation for omega of k, if you look at it, let's focus on this again. So omega of k has a real part and an imaginary part. The real part here just gives the oscillation of your solution with omega, the base frequency of the problem. And then I C1 minus dk squared, if you put this in, this gives you then an exponential term where you have e to the plus C1 minus dk squared. So if the imaginary part of this is positive, you do have a instability. So the imaginary part of omega of k positive, which is equivalent of saying that our wave vector is smaller than C1 over D, then you have that z equal to 0 is linearly unstable. That's this band of modes that starts from 0 and extends to the upper bound C1 over D in wave vector space. So now that you know that, let's construct a wave packet or a front solution, C of x and t. And let's compose the front solution by the solution we just found. So let's Fourier back transform an amplitude that we can choose, z hat of k, and here I do have Fourier transform with the plane wave and the dispersion relation omega k t. So keep in mind that we are constructing a solution which is such a front for z as a function of x. And when this front has a certain velocity v, then we can go to the co-moving frame. In this co-moving frame, we are measuring the profile as a function of psi, and psi is x minus the velocity of this front times t. And here I'm taking v star in the direction of x, for example. So with that, you get a profile equation. This front here as a function of our center of mass, traveling in a co-moving frame, is an integral in Fourier space. Our amplitude and these plane wave factors. Right, that's what we have. And we want this in the limit where initial transients have died out. So I'm writing here in the long time limit that t extends to infinity. If this is supposed to be a traveling wave solution, it should keep its shape, right? It should not change its shape at all. So it should be stationary, a stationary solution of that. And we can use that to determine the integral by, as we did this earlier making a saddle point approximation. So we want this integral to have a significant contribution. The most significant contribution comes from those wave vector regions where the phase is stationary. The phase is omega k minus v star times k, taking now v star in the x direction, as I did here in this picture. And I have to evaluate that at my saddle point that I call k star. And for this to have a significant contribution, the phase needs to be stationary. So that means I can invert or solve that for v star. I know what the velocity is. It is the omega of k dk evaluated at our saddle point. Then, if that's the most important contribution, the dominant part of the integral will have some constants that I ignore, and it will have an exponential dependence on this minus I omega k star minus v star k times t. Okay. This is the most dominant contribution to the integral. I said I want this to be a solution that's steady. So I need to have the imaginary part of what I have here on the right-hand side to be 0, because otherwise this would be a growing or shrinking solution. So I want a steady profile. And for that, I need the system to be marginal, meaning that the imaginary part is 0. So the imaginary part of omega at the saddle point needs to be v star times the imaginary part of k star. Okay, here I should write k star, because that's what I'm evaluating the integral. Okay, so from that we have v star equals the imaginary part of omega of k star divided by the imaginary part of k star. And those are the two equations on which I can base my analysis now. One equation tells you that we do have a stationary solution, gives you the dominant part of the integral coming from the saddle point, and the second condition we just derived from stationarity of the problem. Okay, so we can actually work this out now for the case we are interested in. This is the general scheme. Here below you do find the particular realization of that. So the omega that we have is this here. And we combine this dispersion relation now with those two conditions to get the saddle point and, more importantly, the spreading velocity. So from the first condition, from V star equals d omega k star divided by dk at k star, I find the saddle point. From that you get that the real part of k star is 0, and the imaginary part of my saddle point is square root of C1 over D. From the second relation, from V star, so from the stationarity condition, we then get that this is 2 times the square root of C1D. And now that we have that, we can look back into our table and just read off what C1 is in terms of mu and sigma. And then this becomes 2 times the square root of D. Then we have a square root of 1 over 2 mu sigma over 3 mu plus sigma. And that tells us a few important things. First, the spreading velocity that you have here scales like the square root of D. It's a very strong prediction, because if you look at your data and you divide them by square root of D, the D dependence should cancel out. All the D dependence is the square root. Yeah?
So the ratio of m times sigma over 3 and times sigma came from the relation that it has with C1. Okay.
Yeah, so here we use C1 is a function of mu and sigma. That's what we obtain from the slow manifold reduction. And see, that's where it comes in very importantly, because now we know what the dependence on mu and sigma is. In the microscopic model, in the simulation, we can vary mu and sigma, and we can check the validity of that. Okay, so this dependence is very universal. It doesn't matter what C1 actually is. This here is specific for the May-Leonard model. And what you see, for example, is take sigma as our time scale, and sigma is 1. And then you change mu. So at first, this will change with mu as the square root of mu. And then when mu is very, very large, this should saturate. So that means when I plot this as a function of mu, it should increase first and then saturate. Yeah, maybe we look at that right away. So here, just look on the left-hand side. You see the velocity divided by the square root of d. This is this factor. And then plot it as a function of the reproduction rate mu for a time scale sigma that's chosen to be 1. That's not a restriction, it's just fixing the time scale. These data points that you see, they are obtained by solving the May-Leonard equation, even the stochastic version of the May-Leonard model. So we went 2 steps. We went to the continuum version in terms of this diffusion reaction equation, and we went down on the slow manifold, and still the red line, the prediction coming from the slow manifold reduction without fit parameters, right? This is really using the microscopic rates, fits the data quite well. Not perfectly, but really quite well. All right, so that works. This one comes next. Next question is, what about the wavelength and the frequency of these waves? So how broad are the arms in the spirals, and what's the frequency? So here, I cannot just get away with looking at the linear part, because now I need to worry about how the wavelength is actually selected in the system. And wavelength selection happens when you go to the nonlinear theory. So, but still, let's say we make an ansatz also for the nonlinear theory, which is of the same structure as before. Now let's take Z to be a constant, not depending on K. And let's write it in the same way as e to the minus I omega t minus I k times r, and insert that ansatz into our complex Ginzburg-Lambda equation, so here. And when you insert it there, you see you recover just the linear part as we had it before. And on top, you also get now contribution from the nonlinear term. So from that, you get omega of k is now omega plus I C1 minus dk squared. That's something we had. And then we get from the nonlinear part complex I plus C3 Z squared. Okay. So we still need, for this reasoning that we have, that our solutions are steady states, meaning they are marginal. So the imaginary part of this dispersion relation, which is a one now for the nonlinear theory, should still have a marginal imaginary part. Okay, so this is real plus I times imaginary part, and I want this to be 0 for my system to be steady. If you do so, and you divide up this in real and imaginary part, you'll see that there is this as an imaginary part, and you have C2I Z squared as the imaginary part. So this condition here gives you a condition on the amplitude. So the imaginary part of omega equal to 0 implies that my amplitude will be 1 over C2, C1 minus dk squared. Now you take that and insert that into the dispersion relation, omega of k, such that you then get the real part of our dispersion relation, which is omega, and that's again just the natural oscillation of our system. And now the nonlinear part is this. Okay. And this nonlinear part has to do with the fact that you have now a traveling wave that runs through the system. So in addition to having this oscillation, which is local, you have a oscillation that comes from the fact that your wave is running past you. That means this structure here will select a wavelength such that this is omega plus your spreading velocity times k. This is the condition for selecting a wave number k star of the pattern. We do have V star. I just wrote it above, right? V star is this relation that depends on square root of d at mu. So from that now, the selected wave number for our system, okay, I call this not K star, but K selected. This will be, by solving the equation I wrote it on the upper board, this is square root of C1 divided by C3, square root d, 1 minus square root 1 plus C3 squared. And you now could insert the relation for the parameters. So you could use again what C1 is. You could again use what C3 is. And then you would find that this is a function of d, mu, and sigma. I'm not writing it out because it would be quite lengthy. The important point is we know it as a function of these three variables. You can also then calculate the corresponding frequency for patterns with that selected wave number. And that is then omega plus 2c1 over c3, 1 minus square root 1 plus c3 squared. And again, this is a omega selected as a function of d, mu, and sigma. Okay. Now let's compare again with what is found from the numerical simulations. Okay, here you see the data points from the stochastic simulation that Tobias did at that time. This is the data, and the curve I just calculated is not the blue one, it's actually the red one. So it's off, it's not quite the same thing. The blue one is obtained if you take that relation and just multiply it with a prefactor. Turns out to be a prefactor of 1 over 1.6, and then you get the blue line. So the analytic calculation is not right exactly in terms of the amplitude, but it's perfectly right in terms of dependence on square root of d and the functional dependence on the rate mu for the reproduction. So again, this works quite nice and really means that this complex Ginzburg-Lambda description that you have here is a very well-founded description of the complex dynamics on the slow manifold. All right. Questions? Yeah?
This 1 over 1.6 comes from the linear regularization we took in handling the nonlinear part.
So the 1.6, I think, has its main origin in the stochastic dynamics that I completely ignored. And also, of course, a slow manifold reduction is never really perfect, but the main reason is that these are stochastic simulations that you compare with. Yeah? Other questions? Yeah?
And also, in the normal form of the complex Ginzburg-Lambda equation, there we can have a complex diffusion coefficient. But here, we only we restrict d to a...
Okay, good question. So here, because we know the ground truth is the May-Leonard model. There the diffusion coefficient is real, and there's no reason to assume any kind of complex diffusion coefficient as you map this to a complex Ginzburg-Lambda. Because the set in the end is a linear combination of the other ones, right? So nothing really happens at this level. There are other models where the reduction leads to some complex diffusion coefficient, but not here. Yeah. Okay, so in the end, on this, so dynamics reduces to this slow manifold, and on that slow manifold, it's mainly the vicinity of this fixed point here, which is unstable, that determines the behavior. Then note there was a second approximation. I took the slow manifold in quadratic approximation. So if the system shows excursions which go far out from the center of this manifold to the boundary, then this is wrong. So higher order terms will kick in. And they may also contribute to the error we make in calculating the wavelength. There's y to the third terms, and then once you go up, things become more complicated because this system has boundaries. Yeah. All right. That's it for the May-Leonard model. Let's have a break and then start discussing what happens if frequencies are random and not fixed like we have it here.